Welcome to the 6808 DALI team's final presentation for Spring 2020. My name is Jeremy Cowhan, and my teammates are Olivia Siegel and Ruming Fang. As the demand for energy increases and the threat of climate change becomes urgent, the need for smart energy management systems is apparent. There are a number of players innovating in this space, from Google and its Nest products to Philips and its smart lamps. However, something all modern electrical systems lack is direct integration with digital technology on an infrastructural level. In other words, current smart home energy management systems are abstracted to the appliance or device level as opposed to the system level. In this project, we aim to demonstrate the viability of system-level integration by implementing the Digital Addressable Lighting Interface, or DALI standard. So let me go into how exactly we did this. So the central component of our system is this Arduino you can see here. It communicates via communication bus with our DALI light, which you can see here. Now this DALI light is connected to home power, which is much higher wattage than the Arduino could provide. And by applying a voltage to this NPN transistor, we can close its logic gate and send a digital 1 to our DALI light. And if we remove that voltage, we can send a 0. Now using this protocol down here, we're able to address the light and send it a command with 16-bit signal. Now over on the right, we have our sensing component. Now that was built by Ruming, who is currently in Asia, and this system is able to position a user in a room to identify which light or lights to turn on or off. Now, in order to get that information to the central Arduino, which is in the US, we had the devices communicate over the internet, and of course they used Wi-Fi to do so. With a client-server model, where the US Arduino was the server and the Asia Arduino was the client. Now, the final component of our system was an iPhone app. Now, this app was able to communicate with the Arduino we used for light actuation via BLE, and was able to control things like mode, whether we want to control automatically using the sensors, or whether we want to control manually with, say, an on-off switch in the app. So this is an overview of our system. Now we'll go into some evaluation metrics.
The sensing module that we built to localize consists of an Arduino MCU connected with a low-cost, off-the-shelf ultrasonic sensor. For portability, the module is powered by a 9-volt battery. The module is capable of connecting to a smartphone via BLE, and upon successful connection, it can take high-frequency reading of ultrasonic signals, calculate the distance to the nearest reflector using the signal's round-trip time, and sends the distance data to the phone where the reflector's location is computed by taking into account of the position and angle of the sensor module. To test the module, I fix it at a place above my door at about 2 meters in height to ensure that the sensor can detect a good range of locations without being obstructed by fixed objects in the room. The sensor is also tilted downwards at an angle of about 60 degrees to the vertical line such that it can receive reflections from regular human. In this experiment, I start from my door where the module is installed and walk towards the inside of my room at a steady pace. At the same time, my phone connects with the Arduino, receives the distance readings, and calculates my positions in the room. Using a modified version of the Anteater app, we're able to read off my estimated positions from the phone screen. As it shows, when I'm moving forward, my phone records locations that correspond with my movement along the X directions in the room. One important aspect of the system is its ability to measure locations of the user in the room. Therefore, we take two important metrics, coverage and accuracy, into our consideration. Fortunately, The floor of my room is overlaid by square tiles of 0.4 meter side length. That makes my room a grid by which I can measure coverage and accuracy by taking readings at each cell. First of all, I exclude some locations with large fixed objects such as large shelves and tables. Then I take locational readings at the center of each tile, and the coverage of sensor is given by the ratio between the number of tiles with reasonable location estimates and the total number of tiles. Additionally, we use mean error, which is the average error between estimated values and ground truth, to assess the accuracy of localization. When there is only one sensor module placed in a room, it provides good coverage of only half of the room, probably due to the straight propagation of ultrasonic signals. The coverage is 47.2%, and the mean error is slightly above 20 centimeters. When another sensor module is added, most of the living space in the room are covered, with a percentage of 94. At the same time, the mean error of estimation remains stable at 0.239 meter, which is reasonable accuracy for adjusting lighting in the room. Therefore, with the addition of rather inexpensive sensing capacity, we're able to provide good localization coverage and accuracy sufficient for adjusting ambient environments.
So we're going to show the functionality between the iPhone and the Arduino via Bluetooth. So the user is going to press on. And immediately when you go here it says turned on. This is the serial monitor for the Arduino. And now, user, can you please press turn off? Oh, he accidentally pressed on at first. But then he pressed turned off.
They're so close together.
Oh, that is a functionality that we should fix, right?
Can you move the off further away and make the buttons bigger?